There is a number that ends the conversation before it begins. 9.46 trillion kilometers. That is how far light, the fastest thing the universe permits to exist, travels in a single year. Not a decade, not a century, 1 year. And the nearest star to our sun, Proxima Centauri, sits 4.24 of those years away. 4.24 light years. At the speed of the fastest spacecraft humanity has ever launched, the Parker Solar Probe, which reached a peak velocity of roughly 690,000 kilometers per hour during its closest solar approach, it would take approximately 6,900 years to reach that star. Not 6,900 days, 6,900 years. Bronze Age civilizations were writing their first legal codes when that journey would have had to begin, just to arrive now, and Proxima Centauri is the neighbor. The closest one. The star next door. The Milky Way galaxy stretches across 100,000 light-years. The Andromeda Galaxy, the nearest large galaxy to our own, lies 2.5 million light-years away. The observable universe, the portion of existence that light has had time to reach us from since the Big Bang, spans approximately 93 billion light-years in diameter. These are not poetic exaggerations. These are the measured, verified, peer-reviewed dimensions of reality, confirmed by decades of astronomy, satellite data, and the physics of light itself. Most people, when confronted with these numbers, treat them as curiosities. Impressive, certainly. Humbling, perhaps, but ultimately abstract, the kind of figures you read on an infographic, nod at, and forget over coffee. What almost nobody pauses to do is follow the implications of those numbers to their logical, unforgiving conclusion. If the distances are real, and they are, then the dream of humanity spreading across the stars is not a challenge of engineering. It is not a problem of funding, political will, or technological ambition. It is a collision with the most fundamental laws of physics, laws that have never been broken once in the 4.5 billion year history of this solar system, laws that are as close to absolute truth as science has ever produced. The universe is not big in the way a continent is big, or an ocean, or even a planet. It is big in a way that defeats every intuitive framework the human mind possesses. When astronomers say a star is far, they are not speaking in the casual register of someone describing a long drive. They are describing separations so extreme that the very concept of travel, of departure and arrival within a human timescale, begins to dissolve. Consider the analogy that physicists and science communicators have returned to for generations, not because it is perfect, but because nothing better exists. If you were to shrink the sun down to the size of a standard basketball, roughly 24 centimeters in diameter, the Earth on that same scale would be a small glass marble, roughly 2.2 millimeters wide. And that marble would be sitting 26 meters away from the basketball. 26 meters. The length of a standard school bus, roughly doubled. On this basketball sun scale, the moon would be a tiny grain of sand orbiting that marble at a distance of about 6 centimeters. You could hold the entire Earth-Moon system in the palm of your hand. Now keep that scale. Walk outside with your basketball sun. Your marble Earth is 26 meters away. Where is Proxima Centauri on this scale? 7,000 kilometers away. On a model where the sun is a basketball sitting in your living room, the nearest star is somewhere on the other side of the planet, roughly the distance between Sao Paulo and Helsinki. And that is the closest star, not a distant one, not one near the edge of the galaxy, the closest one. The Milky Way, on that same basketball scale, would stretch for a diameter of approximately 710 million kilometers, nearly 5 times the real distance between the Earth and the Sun. The galaxy itself, on a scale where you can hold the Earth in 2 fingers, would be larger than the orbit of Jupiter. There is no analogy that makes the universe feel manageable, because it is not manageable. The universe was not constructed with human transit in mind. For most of recorded history, this was not a crisis. Humanity did not know the stars were other suns. To ancient Mesopotamian astronomers, Greek philosophers, and medieval Islamic scholars charting the heavens with instruments of extraordinary precision, the stars were lights. Fixed, mysterious, possibly divine, but fundamentally not destinations. The question of whether one could go to them was no more pressing than asking whether one could swim to the moon's reflection in a river. The conceptual revolution came gradually, then all at once. In 1600, Giordano Bruno was burned at the stake in Rome, in part for proposing that the stars were distant suns, each potentially surrounded by their own worlds. The Church found the idea theologically intolerable. The cosmos, many believed, was a stage built for humanity, and a stage does not need to be infinite. Then came the telescopes. Galileo's observations in 1609. Parallax measurements in the 19th century that first allowed astronomers to calculate actual stellar distances with geometry rather than guesswork. The work of Henrietta Swan Leavitt in the early 20th century, who discovered a relationship between the pulsation periods of a class of variable stars and their intrinsic brightness, a discovery that became the first reliable cosmic yardstick, allowing Edwin Hubble to prove in 1924 that the fuzzy smear of light called the Andromeda Nebula was not a gas cloud inside the Milky Way, but an entirely separate galaxy of hundreds of billions of stars, separated from our own by an abyss of empty space that no human technology, no conceivable vehicle could cross in any time frame meaningful to a civilization. The stars were other suns. The galaxies were other Milky Ways. The universe was not a theater built to human scale. It was something else entirely. And yet, paradoxically, the moment science established just how incomprehensibly far away everything was, human beings began dreaming more intensely than ever about going there. The 20th century was the era in which humanity first broke the gravitational hold of its own planet. 12 men walked on the moon, robotic probes visited every major planet in the solar system, and the Voyager spacecraft, launched in 1977, became the first human-made object to cross into interstellar space. It was, by any measure, the most explosive expansion of physical reach in the species' history. Voyager 1 is currently the farthest human-made object from Earth. As of the mid-2020s, it sits roughly 24 billion kilometers away, a figure so large it staggers the imagination. The radio signal it sends back, traveling at the speed of light, takes more than 22 hours to reach us. 24 billion kilometers. And Proxima Centauri is approximately 40 trillion kilometers away. Voyager 1, after nearly 5 decades of continuous travel, has covered roughly 0.06% of the distance to the nearest star. The rocket that carries humans beyond Earth is not a solution to interstellar travel. It is not even a prototype of one. It is a magnificent, extraordinary achievement of engineering that operates, in cosmic terms, at the speed of geological processes. The gap between where we are and where we dream of going is not a gap that ambition and funding can close. It is a gap written into the architecture of space-time itself. And that is where the real story begins. The barrier is not made of metal or politics or money. It is made of physics. Specifically, it is the product of 3 brutal, interlinked realities: the finite speed of light, the exponential energy demands of acceleration, and the biological fragility of the human body in the environment of deep space. Each of these barriers is, on its own, severe enough to end the conversation. Together, they form a wall that no current theory, not ion drives, not nuclear propulsion, not even the most optimistic interpretations of speculative propulsion concepts, has yet found a way around that does not violate either the laws of thermodynamics or the constraints of what a human being can physically survive. What is perhaps most extraordinary is not the scale of the problem. It is how rarely it is stated plainly. Space agencies speak of reaching Mars, then the outer solar system, then interstellar probes, each ambition presented as a natural progression, a ladder of milestones leading in principle to the stars. The popular imagination, shaped by decades of science fiction, treats the cosmos as a frontier, difficult, dangerous, but ultimately open to those with the will to reach it. The physics disagrees, quietly, absolutely, without exception. The universe permits light to cross it. It does not permit us. The speed of light is 299,792 kilometers per second. That number is not a record. It is not a frontier waiting to be pushed. It is a hard ceiling embedded into the structure of space-time itself. A ceiling that, as far as every experiment ever conducted has confirmed, nothing with mass has ever touched, let alone exceeded. Einstein's special theory of relativity, published in 1905, did not merely predict this limit. It explained why the limit exists and why it is permanent. As an object with mass accelerates, its relativistic energy increases. The closer it gets to the speed of light, the more energy each additional increment of acceleration demands. Not linearly, exponentially. The curve does not plateau. It does not level off at some manageable ceiling that a sufficiently powerful engine might one day overcome. It rises toward infinity. To accelerate any object with mass to the speed of light would require an infinite amount of energy. The universe does not contain infinite energy in a usable form. The conversation, at the level of pure physics, ends there. But the more revealing question is not what happens at the speed of light. It is what happens well below it. Take 10% of the speed of light, roughly 30,000 kilometers per second. That is a speed so far beyond anything humanity has ever achieved that it exists currently only in theoretical models and the trajectories of subatomic particles inside particle accelerators. No spacecraft has come remotely close. The New Horizons probe, which flew past Pluto and is now heading toward the outer edges of the solar system, travels at roughly 58,000 kilometers per hour. 10% of the speed of light is approximately 107 million kilometers per hour. New Horizons would need to be moving nearly 2,000 times faster than it currently is just to reach that modest fraction of light speed. At 10% of light speed, the journey to Proxima Centauri would take approximately 42 years. A human lifetime, barely. A crew departing Earth as young adults might arrive, if they survived, as elderly people, or not at all. That is the optimistic scenario. The one that ignores fuel entirely. It does not ignore fuel for long. In 1803, the Russian engineer Konstantin Tsiolkovsky derived what is now called the rocket equation, a relationship between the mass of a spacecraft, the mass of its propellant, its exhaust velocity, and its final speed. The equation is elegant. Its implications are catastrophic. The rocket equation tells us that to accelerate a spacecraft, you must expel mass in the opposite direction. The more you want to accelerate, the more propellant you need. But propellant has mass. And to accelerate that propellant to the point where it can be expelled and generate thrust, you need more propellant still. The relationship is exponential. For every increment of additional speed, the required fuel mass does not merely increase, it multiplies. Run the numbers for a crewed spacecraft attempting to reach just 10% of the speed of light using the best chemical propellant available. Liquid hydrogen and liquid oxygen, the same combination used in the space shuttle's main engines. And the result is not an engineering challenge. It is a mathematical reductio ad absurdum. The fuel-to-payload ratio required would be so extreme that the spacecraft, before it even left Earth orbit, would need to consist almost entirely of propellant. Not 90% propellant and 10% spacecraft, not 99%. The ratio climbs so far past any conceivable structural limit that the exercise becomes physically meaningless. Nuclear propulsion improves the situation. Ion drives improve it further. Theoretical antimatter engines, which would annihilate matter and antimatter to produce pure energy with 100% conversion efficiency, the theoretical maximum permitted by physics, would reduce the required fuel mass dramatically. Even so, a study examining the energy required to propel even a tiny spacecraft toward Proxima Centauri found that at relativistic speeds, the energy demands diverge dramatically depending on the assumptions made, and under realistic conditions remain staggering. There is a reason the numbers remain staggering even with antimatter. Antimatter does not exist in useful quantities anywhere accessible to humanity. The total amount of antimatter produced by all particle accelerators on Earth across all of human history amounts to a fraction of a microgram, enough, if annihilated, to power a small light bulb for a few minutes. Producing antimatter in the quantities a starship would require would demand more energy than the entire civilization currently generates, sustained over timescales measured in centuries. And all of this assumes the spacecraft arrives safely. The interstellar medium, the space between stars, is not empty. It is threaded with gas, dust, and small solid particles distributed at densities that appear negligible until you factor in the speed of a relativistic spacecraft. At 10% of the speed of light, a grain of sand, roughly 1 milligram of mass, would strike the hull with the kinetic energy of a small explosive charge. A pebble, at 50% of the speed of light, would deliver an impact comparable to a small nuclear detonation. The interstellar medium contains far more of these particles than early models assumed. The detection of the interstellar object Oumuamua in 2017, the first confirmed interstellar object to pass through the solar system, and subsequent data has refined estimates of the density of interstellar debris upward. A spacecraft traveling at any meaningful fraction of the speed of light would require shielding massive enough to withstand continuous bombardment from particles that, at those velocities, behave less like specks of dust and more like projectiles fired from a railgun. Heavier shielding means more mass. More mass means more propellant. More propellant means more mass. The equation tightens its grip with every variable you add. Then there is radiation. Deep space beyond the protective envelope of Earth's magnetic field and atmosphere is saturated with high-energy ionizing radiation. Galactic cosmic rays, solar energetic particles, and secondary radiation produced when primary particles interact with a spacecraft's own structure. On the International Space Station, astronauts in low Earth orbit receive a radiation dose roughly equivalent to what a chest X-ray delivers every 5 to 6 days. Beyond the magnetosphere in deep interplanetary space, the dose rate increases significantly. In interstellar space, outside the heliosphere, the bubble of solar wind that partially shields the solar system from the broader galactic radiation environment, it increases further. The human body is not indifferent to this. Long-duration exposure to galactic cosmic rays damages DNA, increases cancer risk, and, in findings that alarmed NASA mission planners preparing for eventual Mars missions, causes measurable changes to the central nervous system. Studies on rodents exposed to simulated cosmic ray environments showed cognitive impairment, structural changes to neurons, and degraded performance on learning and memory tasks. The brain, the most radiation-sensitive organ in the body after the gonads, is also the most operationally critical organ on a crewed spacecraft flying through the interstellar void. No current shielding material solves this problem. Lead, dense as it is, actually makes certain forms of cosmic ray exposure worse because high-energy particles interact with lead nuclei and produce secondary radiation showers. Water is a better shield, mass for mass. But the quantities of water needed to provide meaningful protection over a journey of decades would add so much mass to the vehicle that the propulsion problem becomes even more intractable than before. The three barriers, the energy demand, the interstellar debris field, and the radiation environment, each constitute individually an unsolved problem at the frontier of physics and materials science. No proposed solution for any one of them is remotely close to engineering readiness. No proposed solution for all three simultaneously exists at any level beyond speculation. What the rocket equation began, Einstein completed, and what Einstein completed, the interstellar medium enforces. There is a concept in aerospace engineering called the tyranny of the rocket equation, a phrase used not metaphorically but literally by working engineers to describe the exponential fuel burden that crushes the mass budgets of even modest missions within the solar system. Getting a few kilograms of scientific instruments to Mars requires launching hundreds of tons of propellant from Earth. Getting a crewed vehicle to Mars and back, with life support, radiation shielding, landing systems, and return propellant, requires a vehicle so large that it strains the limits of the most powerful rockets ever conceived. Mars is, on the scale of the galaxy, not a destination at all. It is a feature in the same parking lot. Proxima Centauri is the next parking lot over, separated from ours by approximately 266,000 astronomical units. 266,000 times the distance between Earth and the Sun. Every physical law that makes Mars hard makes Proxima impossible, amplified by a factor so large that the comparison itself borders on meaninglessness. The dream of the stars is not waiting for better rockets. It is running directly into a wall that the universe built before the Earth existed. And here is the part almost nobody discusses. Even if every propulsion problem were solved, if some yet undiscovered physics permitted a spacecraft to accelerate to a substantial fraction of the speed of light without consuming impossible quantities of fuel, without being shredded by interstellar dust, and without irradiating its crew into incapacitation, the journey to Proxima Centauri would still take years. Decades, most likely, at any velocity achievable within known physics. And once the crew arrived at Proxima Centauri, whatever civilization, whatever mission control, whatever version of Earth sent them, would have aged, changed, or ceased to exist in forms they would recognize. Time dilation compounds this. At 90% of the speed of light, time aboard the spacecraft slows to roughly 44% of the rate experienced by an observer on Earth. A crew experiencing a journey of a few years of ship time would return, if they returned, to an Earth where decades had passed. The people who launched them would be old or dead. The institutions that funded them would have changed beyond recognition. The radio signals sent back to Earth during the journey would take years to arrive, each one a message from the past by the time it reached any receiver. This is not science fiction's vision of interstellar travel. It is the physical reality of what Einstein's equations actually predict, verified, tested, and confirmed by atomic clocks flown on aircraft and by the behavior of muons generated in the upper atmosphere, which survive long enough to reach the ground only because relativistic time dilation extends their decay lifetime from the perspective of an observer at rest. The equations work. They have always worked. And they describe a universe in which humanity is, with extraordinary precision, confined. What no one has yet fully reckoned with is what that confinement means. Not just for the ambitions of space agencies and the pages of science magazines, but for the long-term survival of the only civilization known to exist. Because the sun is not permanent, and the Earth, tethered to a star with a finite lifespan, is on a clock that the physics of stellar evolution has been running since before the first cell divided in the first ocean. The Tsiolkovsky rocket equation is not a suggestion. It is not an approximation that future engineering will refine into something more forgiving. It is a direct mathematical consequence of Newton's third law of motion. For every action, an equal and opposite reaction, applied to the specific problem of accelerating a mass through a vacuum where there is nothing to push against except the mass you expel behind you. The equation reads, delta V equals exhaust velocity multiplied by the natural logarithm of the ratio of initial mass to final mass. Delta V is the total change in velocity the spacecraft can achieve. Exhaust velocity is how fast the propellant exits the engine. The ratio inside the logarithm is the wet mass, the spacecraft fully loaded with fuel, divided by the dry mass, the spacecraft empty of fuel. The logarithm is the killer. Logarithms grow slowly. To double the delta V of a spacecraft while keeping the exhaust velocity constant, you do not double the fuel. You square the mass ratio. To triple the delta V, you cube it. The relationship between the velocity you want and the fuel you need climbs so steeply that even modest ambitions in terms of final speed translate into fuel requirements that are physically unrealizable within any structure that can be built and launched from Earth's surface. The Saturn V rocket, still the most powerful launch vehicle ever successfully operated, had a total launch mass of approximately 2,970,000 kilograms. Of that, roughly 2,700,000 kilograms was propellant. The payload delivered to the moon was approximately 45,000 kilograms. The ratio of propellant to useful payload for a lunar mission, the moon, a mere 384,000 kilometers away, was approximately 60 to 1, 60 kilograms of fuel for every kilogram of spacecraft that reached the destination. Mars is, at closest approach, approximately 54 million kilometers from Earth. The moon is 384,000. Mars is, in round numbers, roughly 140 times farther than the moon. The fuel penalty for a crewed Mars return mission, accounting for the need to carry return propellant and land on and depart from Mars's surface, climbs to mass ratios that require vehicles far larger than anything Saturn V could launch, which is precisely why every serious Mars architecture proposed by NASA and private spaceflight companies involves in-space propellant production on Mars using local resources. Without manufacturing rocket fuel on Mars from Martian water ice and atmospheric carbon dioxide, a crewed return mission becomes impossible to launch from Earth in a single vehicle. The destination is 140 times farther than the moon, and the fuel math is already pushing the boundary of what a civilization's industrial capacity can assemble in orbit. Proxima Centauri is 266,000 astronomical units away. 1 astronomical unit is the average distance from the Earth to the Sun, approximately 149,600,000 kilometers. Proxima Centauri is 266,000 times that distance. If the moon mission required a mass ratio of 60:1, and the numbers already strain comprehension for Mars, then running Tsiolkovsky's equation for a destination 4 light-years away, even at a charitable assumed exhaust velocity far beyond any existing or near-term propulsion system, produces a required fuel mass that exceeds the mass of observable matter in the known universe many times over, for any speed that would complete the journey within a human lifetime. This is not rhetorical flourish. The physics library at the University of Maryland published a detailed course analysis of interstellar travel energy requirements that walks through these calculations step by step. The conclusions are not pessimistic interpretations of the data. They are the data. The only escape from Tsiolkovsky's tyranny is to change the exhaust velocity, to find a propellant that exits the engine so fast that the mass ratio becomes manageable. Chemical propulsion, the basis of every rocket ever launched, produces exhaust velocities of roughly 4 to 4.5 kilometers per second for the best available propellants. Ion drives, which accelerate charged particles using electric fields, achieve exhaust velocities of 30 to 80 kilometers per second. Nuclear thermal rockets, which heat propellant by passing it through a nuclear reactor, can theoretically achieve exhaust velocities of around 8 to 9 kilometers per second with solid core designs, and potentially higher with more advanced concepts. Nuclear pulse propulsion, the Orion concept, which proposed detonating a series of nuclear bombs behind the spacecraft to accelerate it, offered exhaust velocities potentially reaching tens of thousands of kilometers per second, making it the most physically credible high-speed propulsion concept ever seriously studied. The Orion project was canceled in 1963, in part due to the Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space. The concept has never been tested at any scale relevant to interstellar flight. Its fuel, nuclear weapons, presents procurement and political problems that dwarf its engineering challenges. And even at its theoretical best, the velocities it could achieve represent a fraction of a percent of the speed of light. Fusion propulsion, which would harness the same energy source that powers stars, offers exhaust velocities potentially reaching several percent of the speed of light. Enough, in principle, to reduce the Proxima journey to a matter of centuries rather than millennia. The obstacle is that controlled nuclear fusion has not yet been achieved at net energy gain in a sustained, repeatable manner on Earth, despite decades of research and billions of dollars of investment. The National Ignition Facility at Lawrence Livermore National Laboratory achieved ignition, a fusion reaction producing more energy than the laser energy delivered to the fuel target, for the first time in December 2022. It was a landmark result. The total energy input into the facility's laser system was still far larger than the fusion yield. Commercial fusion power remains, by scientific consensus, at minimum 1 to 2 decades away under optimistic timelines, and fusion propulsion for spacecraft is an additional engineering leap beyond that. Antimatter propulsion is theoretically superior to fusion. Matter-antimatter annihilation converts 100% of the rest mass of both particles into pure energy, following Einstein's relation between energy, mass, and the speed of light squared. No other reaction releases energy with that efficiency. A kilogram of antimatter annihilating with a kilogram of matter releases energy equivalent to roughly 43 megatons of TNT. For propulsion purposes, if even a fraction of that energy could be directed efficiently as thrust, the exhaust velocities would approach the speed of light itself, and the Tsiolkovsky mass ratios would become manageable for the first time. The production problem is absolute. The CERN Particle Physics Laboratory in Geneva, the largest and most powerful particle accelerator complex on Earth, produces antiprotons at a rate of approximately 10 million particles per second during dedicated antiproton production runs. 10 million antiprotons per second sounds like a large number. The mass of 10 million antiprotons is approximately 16 femtograms, 16 quadrillionths of a gram. At that production rate, manufacturing a single gram of antihydrogen would require approximately 100 billion years. The current age of the universe is approximately 13.8 billion years. CERN would need to operate for roughly 7 times the current age of the universe to produce 1 gram of antimatter fuel. The energy cost compounds the problem. Producing antimatter requires more energy input than the antimatter stores, due to the thermodynamic inefficiency of the production process. Every antiproton produced at CERN costs roughly 10 billion times more energy than it could release upon annihilation. Antimatter is not a fuel in any currently accessible sense. It is an experimental byproduct of high-energy physics research, produced in quantities so minute they are measured in individual particles. Laser sail concepts, most prominently, the Breakthrough Starshot initiative announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, propose a different approach entirely, one that sidesteps the rocket equation by not carrying propellant at all. The idea is to accelerate an extremely small, extremely lightweight spacecraft using a powerful ground-based laser array that pushes against a large reflective sail. Without onboard fuel, the mass ratio problem dissolves. The laser does the pushing from Earth. Breakthrough Starshot's engineering concept calls for a sail spacecraft massing roughly 1 gram, a chip-scale device with minimal instrumentation, accelerated by a laser array with a combined power output of 100 gigawatts, applied for a period of minutes to reach approximately 20% of the speed of light. At that velocity, the journey to Proxima Centauri would take approximately 20 years. The challenges are formidable at every level. 100 gigawatts is roughly equivalent to the total electrical generating capacity of Germany. Focusing and maintaining coherence in a laser beam of that power over the distances required, the beam must push the sail for several minutes as the craft accelerates away from Earth. Requires optical engineering that does not yet exist. The sail must be capable of reflecting that power without being destroyed by it. A 1 gram sail absorbing even a tiny fraction of 100 gigawatts would be instantly vaporized. The spacecraft, once at cruise velocity, is passing through the interstellar medium at 20% of the speed of light. The grain of sand as explosive problem described in the previous section of this film applies with full force. And when the probe arrives at Proxima Centauri after 20 years, it has no way to slow down. With no propellant, no mechanism for deceleration exists. The spacecraft would pass through the Proxima system at 20% of the speed of light, its instruments having a few hours at most to gather data before the star system vanishes behind it. Getting that data back to Earth would take another 4 years at the speed of light. Breakthrough Starshot remains a research program. No prototype sail has been accelerated. The laser array is at the conceptual stage. The funding required to build it at operational scale is estimated in the tens of billions of dollars. As of the mid-2020s, the project's public updates have slowed considerably from its initial announcement. The pattern is consistent across every proposed propulsion concept. At the level of nearest star distances, the absolute minimum interstellar target, every approach either requires energy sources that do not exist in accessible form, materials that cannot yet be manufactured, engineering systems that have not been built, or some combination of all three. None of these barriers is merely a matter of scaling up existing technology. Each represents a qualitative leap into physics or engineering that, in several cases, has not been demonstrated even in principle. Interstellar space itself enforces another constraint that no propulsion system addresses: communication. At the speed of light, a radio signal from Proxima Centauri takes 4.24 years to reach Earth. A spacecraft traveling at 10% of the speed of light and sending a status signal back to mission control would wait 42 years to receive a reply. There is no real-time communication between a spacecraft at interstellar distances and its home civilization. Every decision made during such a journey must be made autonomously by the crew or the spacecraft's systems, with no possibility of consulting Earth. The mission operates in a silence that is not poetic, but absolute. The Sun is a medium-sized yellow dwarf star, currently approximately 4.6 billion years old, roughly halfway through its main sequence lifetime. In approximately 5 billion years, it will exhaust the hydrogen fuel in its core and begin the transition to a red giant, expanding outward to engulf Mercury, Venus, and possibly Earth. Long before that, within roughly 1 billion years, the gradual increase in solar luminosity, as the sun slowly brightens over its main sequence lifetime, will push Earth's surface temperature above the threshold for liquid water. The oceans will begin to evaporate. The atmosphere will undergo a runaway greenhouse process. Life as it currently exists on Earth's surface will become impossible. 1 billion years, a number so large it defies intuition, but a number, not infinity. The countdown has been running since the solar system formed. The question of whether humanity can leave Earth is not, at its deepest level, a question about adventure or exploration. It is a question about whether the only known repository of minds in the universe has a mechanism for its own continuation when the star it orbits completes a process it has already begun. The physics says the door is narrow. What the next layer of this story reveals is whether it is merely narrow or whether it is welded shut from the outside. In 1915, Albert Einstein completed the general theory of relativity. The special theory, published a decade earlier, had established the speed of light as an absolute speed limit for matter and energy. General relativity went further. It described gravity not as a force transmitted through space, but as the curvature of space-time itself, a geometric distortion produced by mass and energy, through which all objects, including light, travel along the straightest possible paths. The universe was not a stage on which physics happened. The universe was the physics. Space and time were not fixed containers. They bent, stretched, compressed, and warped in response to the matter and energy they contained. The equations were extraordinary. They predicted phenomena that Newton's gravity could not: the precise precession of Mercury's orbit, the bending of starlight around massive objects, the existence of gravitational waves, the expansion of the universe. Every prediction has since been confirmed by observation, some with extraordinary precision. The detection of gravitational waves by the LIGO collaboration in September 2015, announced in February 2016, matched the predictions of general relativity to within the measurement errors of the instruments. Instruments capable of detecting a distortion in spacetime 1/10,000th the diameter of a proton across a 4-kilometer laser interferometer. General relativity works, completely, consistently, across every scale at which it has been tested. And embedded within those same equations, in a region of solution space that Einstein himself initially dismissed, was a mathematical structure that seemed, for a brief period in the 20th century, to offer a way around everything. A loophole, not in the physics, but inside the geometry of space-time itself. In 1935, Einstein and his colleague Nathan Rosen published a paper describing what their equations implied about the geometry of a black hole's gravitational field. Their analysis showed that the singularity at the center of a black hole, under certain idealized conditions, could be mathematically connected to another region of spacetime through a bridge, a tunnel-like structure threading through the fabric of the universe. Einstein and Rosen did not use the word that would later define this concept. That word came from the physicist John Wheeler, who in 1957 coined the term wormhole to describe these theoretical Einstein-Rosen bridges. A wormhole, in the simplest geometric description, is a shortcut. 2 points in the universe that are separated by billions of light years in normal three-dimensional space could, if connected by a wormhole, be physically adjacent through the tunnel. A spacecraft entering one mouth of the wormhole would emerge from the other, having traversed an effectively zero distance through the tunnel, while the normal space distance between the 2 points remained unchanged. The speed of light would not be violated. The spacecraft would not accelerate beyond the light barrier. It would simply take a different path through the geometry of spacetime, one that the geometry, under certain conditions, permits. The physics community's response to this was not immediate dismissal. The equations allowed it. That was not trivial. For decades, theorists examined wormhole solutions with serious rigor. The obstacles emerged systematically, and they were severe. The first problem was stability. The original Einstein-Rosen bridge is not traversable. It forms and collapses faster than light could pass through it. In theoretical terms, in a time so short that no signal, no matter how fast, could transit the tunnel before it pinched shut. A wormhole that cannot be kept open long enough for anything to pass through it is not a transportation system. It is a mathematical curiosity. In 1988, Physicists Kip Thorne and Michael Morris, working at the California Institute of Technology, published a landmark paper in the American Journal of Physics, examining the conditions under which a wormhole could theoretically be kept open and traversable. Their analysis was rigorous, and its conclusion was unambiguous. Maintaining a traversable wormhole requires the presence of exotic matter, a substance with negative energy density. Negative energy density is not merely exotic in the colloquial sense. It is a physical property that no known form of matter possesses. Normal matter, dark matter, radiation, all of these have positive or zero energy density. A substance with negative energy density would have, in a precise technical sense, less than nothing. The gravitational effect of negative energy density is repulsive. It pushes space-time outward, which is precisely what would be needed to hold a wormhole throat open against its natural tendency to collapse. The Casimir effect, a real, measured quantum mechanical phenomenon in which two uncharged parallel conducting plates placed extremely close together in a vacuum experience a small attractive force, does produce a region of negative energy density in the space between the plates. It was briefly discussed in the context of wormhole stabilization. The quantities of negative energy involved in the Casimir effect are extraordinarily small, many orders of magnitude below what any wormhole throat of traversable size would require. Scaling the Casimir effect to the amounts needed for a macroscopic wormhole faces no known physical pathway. The effect exists, but its magnitude at any achievable plate separation is negligible for this purpose. The second fundamental problem arrived in 1992 in a paper by Stephen Hawking. Hawking demonstrated that any traversable wormhole that also allowed faster-than-light effective transit, even through the geometric shortcut mechanism rather than by exceeding light speed locally, would simultaneously allow the construction of a closed time-like curve, a path through space-time that loops back to its own starting point. A traversable wormhole is, in the language of general relativity, a time machine. It does not merely connect 2 points in space. It connects 2 points in space-time, meaning the exit mouth could be located not just at a different place, but at a different time than the entry mouth. This led Hawking to formulate what he called the chronology protection conjecture, the hypothesis that the laws of physics conspired to prevent the formation of closed time-like curves, and therefore prevent the formation of traversable wormholes, because the alternative leads to causality violations of the kind that make consistent physical description of a system impossible. While the conjecture has not been formally proven, it remains a hypothesis. Every attempt to construct a traversable wormhole in theory has either required negative energy in quantities that violate quantum field theory constraints, or has produced instabilities driven by quantum vacuum fluctuations that destroy the wormhole before it can be used. In 2022, a team of researchers, including theoretical physicists from Harvard and other institutions, published results in the journal Nature, describing what they called a traversable wormhole simulation performed on the Google Sycamore quantum computer. The announcement generated significant press coverage and considerable excitement. The characterization was, in scientific terms, dramatically overstated. What the experiment actually demonstrated was a simulation of a quantum gravity model known as the Sachdev-Ye-Kitaev model, implemented on a quantum processor with 9 qubits. The simulation showed that quantum information encoded on one side of the system appeared on the other side after a specific quantum teleportation protocol was executed, a result consistent with the theoretical framework of the model. The experiment involved no actual physical wormhole, no actual space-time curvature, no actual traversal of space by any physical object. It was a quantum information experiment that used a wormhole as a conceptual framework for describing certain quantum entanglement phenomena. The distinction is not semantic. No space-time geometry was manipulated, no tunnel through space was opened, no physical object was transported anywhere. Numerous physicists, including some of the researchers involved in the study, noted publicly in subsequent coverage that the headline characterization, that a wormhole had been created, was misleading. The experiment was significant in the context of quantum gravity research and the relationship between entanglement and spacetime geometry, known as the ER equals EPR conjecture proposed by Maldacena and Susskind in 2013. It demonstrated nothing about the feasibility of interstellar travel. The warp drive had a parallel trajectory. In 1994, Mexican physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity describing a metric, a solution to Einstein's field equations, in which a region of flat spacetime could be enclosed in a bubble that contracted space in front of it and expanded space behind it. The bubble itself would move through space, carrying its contents at arbitrarily high velocity. The object inside the bubble would experience no local violation of the speed of light. It would be stationary relative to the space immediately around it. The spacetime itself would be doing the moving. The Alcubierre drive, as it became known, was immediately recognized as a serious mathematical solution to the field equations. Einstein's equations permit it. It does not require the occupant to accelerate through local spacetime. It does not impose relativistic time dilation on the crew. It does not, in principle, violate causality in the direct sense that a wormhole does. The exotic matter requirement returned immediately. Alcubierre's original calculation estimated that operating the warp bubble would require a quantity of negative energy equivalent to the mass energy of approximately the mass of Jupiter, in negative form. In subsequent years, Harold White at NASA's Johnson Space Center published analyses suggesting that modifications to the bubble geometry could reduce this requirement substantially to quantities theoretically closer to grams of exotic matter rather than Jupiter masses. White's work generated considerable media attention and led to NASA allocating a small laboratory effort, the Advanced Propulsion Physics Laboratory, informally called EagleWorks, to exploratory research. In 2021, a more rigorous analysis by physicist Eric Lentz at the University of Göttingen proposed warp drive solutions that appeared not to require negative energy, using soliton-like structures within positive energy distributions. It was a significant theoretical refinement. The energy requirements in Lentz's model, however, remained staggering, on the order of the mass energy equivalent of a mass larger than Jupiter, now in positive form rather than exotic matter, but still physically inaccessible. A separate 2022 study by Bobrick and Martyr established a general framework for classifying warp drives and demonstrated that all physically consistent warp drive geometries either require exotic matter or require energy conditions that no known physical process can satisfy. The pattern across wormholes, warp drives, and every other proposed mechanism for circumventing the light speed limit shares a common structure. General relativity permits these solutions mathematically. The field equations do not prohibit them. The prohibition comes from a deeper layer, from quantum field theory's constraints on the existence and magnitude of negative energy, from thermodynamic limits on energy availability, and from the behavior of quantum vacuum fluctuations near exotic spacetime geometries. The mathematics of general relativity describes what spacetime can do. The physics of matter and energy describes what we can actually build inside it. What no spacetime geometry can fix is the biological clock. In the years following the Apollo program, as the scientific community began systematic assessment of the physiological effects of spaceflight on human health, the data accumulated in directions that no mission planner had fully anticipated. Bone density loss in microgravity follows a measurable curve. Astronauts on the International Space Station lose approximately 1 to 2% of bone mineral density per month in weight-bearing bones, despite rigorous daily exercise protocols designed specifically to counter it. The rate of loss slows over long missions, but does not stop. Scott Kelly, who completed a nearly year-long mission aboard the ISS in 2016, the longest American spaceflight at the time, showed measurable bone density changes, cardiovascular deconditioning, and changes in visual acuity caused by elevated intracranial pressure, a condition now understood to affect the majority of long-duration astronauts and caused by the cephalad fluid shift that occurs in the absence of gravity. Kelly's vision required correction for years after landing. The twin study conducted with Scott Kelly and his identical twin Mark Kelly, Mark remaining on Earth as a ground-based control subject, produced one of the most detailed datasets ever assembled on long-duration spaceflight effects. Gene expression patterns changed. Telomere length fluctuated in unexpected ways during and after the mission. Cognitive performance on certain tasks showed measurable changes during flight. Most markers returned toward baseline after return to Earth, but not all. The study's authors noted explicitly that the data raised unresolved questions about the biological sustainability of missions lasting far longer than 1 year. The nearest star requires a journey measured not in months, but in decades, centuries, or millennia, depending on the propulsion system assumed. No amount of exercise protocol addresses that arithmetic. No pharmaceutical intervention currently known prevents cumulative radiation damage to the central nervous system over a decade of continuous exposure to the galactic cosmic ray background. No biomedical intervention currently known maintains human musculoskeletal health through decades of microgravity without a gravitational field. And generating a gravitational field aboard a spacecraft requires either rotating the vessel continuously, which introduces engineering complications, or accelerating continuously at 1g, which brings the energy demands of Tsiolkovsky's equation back with full force. The universe built no exceptions into any of this. The laws are not awaiting revision. They are, within the domain of all confirmed physical observation, complete. The great theoretical loopholes, the ones that briefly made the stars feel accessible on paper, have each resolved under sustained scientific examination into the same answer. The geometry permits the dream. The physics of matter does not. And yet something happened in the early 21st century that none of the physicists calculating rocket equations or wormhole stability conditions had placed at the center of their models. Something that changed not the physics of interstellar travel, but the terms of the question entirely. The sun has been burning for 4.6 billion years. Every second it converts approximately 600 million tons of hydrogen into helium through nuclear fusion in its core, releasing energy as gamma rays that take tens of thousands of years to migrate outward through the radiative zone before emerging at the surface as visible light. That light reaches Earth in 8 minutes and 20 seconds. It has been doing this without interruption since before the first complex molecules assembled themselves in the early oceans of this planet. The Sun is, by the standards of stellar physics, a stable and unremarkable star. Its position on the Hertzsprung-Russell diagram, the foundational classification chart of stellar properties, places it squarely in the middle of the main sequence, the broad diagonal band where stars spend the majority of their lives in a state of equilibrium between the inward pull of gravity and the outward pressure of nuclear fusion. Main sequence stars are the universe's most reliable long-term energy sources. They do not explode unpredictably. They do not flicker. They burn with a consistency that, over billions of years, permitted liquid water to persist on a rocky planet at the right orbital distance long enough for evolution to produce, among other things, the nervous systems now contemplating the sun's eventual fate. That fate is not in question. It is determined by physics that operates without exception across every star of the sun's mass and composition that has ever existed. As the sun burns hydrogen in its core, the helium ash produced by fusion accumulates. Helium does not fuse at the temperatures currently sustained in the solar core. It requires higher temperatures than hydrogen fusion, temperatures the core cannot yet reach. The accumulating helium forms an inert central region that gradually compresses under gravity. As it compresses, it heats. As the surrounding hydrogen shell heats, fusion accelerates. The sun brightens. This process has been operating continuously since the sun formed. The sun today is approximately 30% more luminous than it was when it first ignited on the main sequence. Over the next approximately 1 billion years, it will brighten by a further 10%. That increment of 10% additional solar radiation is not merely warm. It is, for Earth's climate system, catastrophic. Climate models incorporating the gradual increase in solar luminosity project that within approximately 600 million to 1 billion years, the increase in solar energy input will push Earth's average surface temperature beyond the threshold at which the carbon silicate cycle, the long-term geological thermostat that has regulated Earth's atmospheric carbon dioxide concentration for billions of years, breaks down. The silicate weathering rate will decline as temperatures rise, carbon dioxide will accumulate, and a positive feedback loop will drive temperatures higher still. The oceans will begin to evaporate. Water vapor, a potent greenhouse gas, will amplify the warming further. The upper atmosphere will become saturated with water vapor, which will be photodissociated by ultraviolet radiation, split into hydrogen, which escapes to space, and oxygen. the oceans will be lost. 1 billion years. Not 5 billion, the commonly cited figure for the sun's eventual red giant phase. 1 billion. The surface sterilization of Earth by its own star's natural evolution begins in roughly 1 billion years under current models. Life as it exists today, dependent on liquid water, moderate temperatures, and a stable atmospheric chemistry, faces a deadline that is not geological in the vague sense of being immeasurably distant. It is a specific, calculable number derived from well-understood stellar physics and climate science. 1 billion years from now, if the planet remains in its current state, no ocean will exist on its surface. For context, complex multicellular life appeared on Earth approximately 600 million years ago. The entire history of animals, plants, fungi, and every complex organism that has ever lived on this planet fits inside a window of 600 million years. The remaining habitable window, 1 billion years, is longer, but it is finite, and it is closing at a rate of 1 year per year. The Sun's main sequence lifetime ends in approximately 5 billion years from now. At that point, the core hydrogen is exhausted entirely. The core contracts rapidly under gravity, while the outer layers, responding to the increased energy output of the hydrogen-burning shell around the inert helium core, expand dramatically outward. The Sun becomes a subgiant, then a red giant. Its outer atmosphere expands to a radius that current models estimate will engulf Mercury and Venus, and potentially reach the orbit of Earth, though the precise extent of the expansion depends on mass loss rates during the red giant phase that carry significant uncertainty in current stellar models. Whether Earth's surface is physically absorbed by the expanded solar atmosphere or merely scorched at extreme close range by a star orders of magnitude more luminous than today, the result for any surface biosphere is identical. Nothing survives. The helium flash occurs when the degenerate helium core reaches sufficient temperature to ignite helium fusion, a runaway thermonuclear event releasing enormous energy in a very short time, though one that occurs deep within the stellar interior and produces no dramatic external explosion. The Sun then enters the horizontal branch phase, burning helium in its core more quietly for approximately 100 million years. Then the helium is exhausted. The core contracts again. The outer layers expand again, even more dramatically this time. The Sun becomes an asymptotic giant branch star, pulsating and shedding its outer layers as stellar winds. Those expelled layers form a planetary nebula, a glowing shell of ionized gas expanding outward through the surrounding space, illuminated by the ultraviolet radiation of the hot stellar remnant at its center. What remains of the Sun after the planetary nebula disperses is a white dwarf, a sphere roughly the size of Earth, composed almost entirely of electron-degenerate carbon and oxygen, with no ongoing nuclear fusion, radiating away its residual heat into space over billions of years. It will cool. After hundreds of billions of years, a timescale longer than the current age of the universe, it will fade below detectability. A black dwarf. Cold. Dark. The Sun's entire nuclear fuel supply used. The solar system will still exist at that point, in some form. The outer planets, Jupiter, Saturn, Uranus, Neptune, will likely survive the red giant phase with their orbits altered by the Sun's mass loss, but their structures intact. The asteroid belt will be disturbed. The Kuiper belt and Oort cloud will be stripped outward. The white dwarf Sun will exert a gravitational grip on whatever remains, holding a cold, dark system of surviving worlds in orbits around a cooling ember. This is the destination of every atom on Earth's surface, on the current trajectory if nothing changes. Not destruction in the sense of an explosion, not a sudden catastrophe, but a slow, inexorable withdrawal of the conditions that permit chemistry to sustain itself at the temperatures required for biology. The window does not slam shut. It dims over geological and stellar timescales until no light comes through. There are approximately 8 billion people alive on Earth today. There have been, by various demographic estimates, somewhere between 100 and 110 billion human beings who have ever lived since the emergence of anatomically modern Homo sapiens approximately 300,000 years ago. Every one of those lives, every structure ever built, every piece of music ever composed, every scientific discovery ever made, every language ever spoken, every institution ever founded, All of it has occurred within the first 0.03% of the remaining habitable window on this planet. The mathematical reality is precise. If complex life on Earth has a remaining tenure of roughly 1 billion years, and humanity has existed for approximately 300,000 years, then our species has consumed roughly 0.03% of the time budget available to life on this world under current stellar conditions. We are, in cosmic terms, extraordinarily early. The window is not closing fast, but it is closing. And the physics established in Acts 2, 3, and 4 of this film describes a civilization that has, as yet, no confirmed mechanism for leaving before it does. The urgency is not immediate in any human timescale. No one alive today, no one's children or grandchildren or descendants across thousands of generations will witness the oceans beginning to evaporate. The deadline is so far in the future that the gap between 1 billion years and 2 billion years is itself larger than the entire history of complex animal life on Earth. The habitability crisis of solar brightening is not a problem for any civilization that resembles ours. It is a problem for whatever this civilization eventually becomes, or fails to become. The proximity of the crisis, in cosmic terms, is the point. Stars in the Milky Way have been forming, burning, and dying for approximately 13 billion years. In that time, countless stellar systems have passed through the same sequence the Sun is now executing. Rocky planets and habitable zones around Sun-like stars have been rendered uninhabitable by stellar evolution on timescales that, from the perspective of the galaxy, are not unusual or extraordinary. They are the standard outcome. The galaxy is full of the ruins of what were once presumably habitable conditions. Dead worlds orbiting white dwarfs, scorched remnants of planetary surfaces that once lay in temperate zones, systems that experienced precisely what the Sun-Earth system will experience, simply earlier in the galaxy's history. Whether any of those systems ever produced civilizations is unknown. The Fermi paradox, the silence of the cosmos in response to decades of radio searches conducted under the Search for Extraterrestrial Intelligence programs, has no confirmed resolution. The Great Silence, as it is sometimes called, admits many explanations. Civilizations may be rare. Radio communication may be a brief technological phase that advanced civilizations pass through and beyond quickly. The galaxy may be a place where intelligence emerges and then, predictably, runs into the same walls described in this film and fails to surpass them. The distances are the same for everyone. The physics is the same for everyone. The stellar clocks are the same for everyone. The Kepler Space Telescope, launched in 2009 and retired in 2018, identified over 2,600 confirmed exoplanets during its operational lifetime, with thousands more candidates awaiting confirmation. The James Webb Space Telescope, operational since 2022, has begun characterizing the atmospheres of some of these worlds, detecting carbon dioxide, water vapor, methane, and other molecules through transmission spectroscopy as planets transit their host stars. The data is preliminary. No biosignature has been confirmed. No atmosphere has been identified that unambiguously requires a biological explanation. The search continues, and the sensitivity of the instruments will improve. What Kepler established beyond any statistical doubt is that rocky planets in the habitable zones of their stars are not rare in this galaxy. The initial estimates suggested that something on the order of 20 to 40% of Sun-like stars host at least one planet in the habitable zone. The Milky Way contains approximately 200 billion stars. Even conservative estimates imply billions of potentially habitable worlds in this galaxy alone. The universe contains an estimated 2 trillion galaxies. The universe is not hostile to the conditions that produce life. It appears, from the evidence available, to produce those conditions routinely, at enormous scale. And yet not one of those 2 trillion galaxies has sent a signal we have detected. Not one of those billions of potentially habitable worlds has produced a civilization that has reached us. The radio telescopes have been listening since 1960, when astronomer Frank Drake pointed the 85-foot antenna at the National Radio Astronomy Observatory in Green Bank, West Virginia, at the stars Tau Ceti and Epsilon Eridani, and recorded nothing but static. 65 years of listening. One confirmed anomaly, the WOW signal detected in 1977 at Ohio State University's Big Ear Radio Telescope, a 37-second burst of narrowband radio emission at the hydrogen line frequency that has never been explained and never repeated. Nothing else. The silence is not proof of absence. It is not evidence of any particular explanation. But set against everything established in this film, the distances, the energy demands, the biological constraints, the theoretical dead ends, it carries a weight that is difficult to dismiss. The physics that traps us may trap everyone. The rocket equation is not a human invention. It is a consequence of Newton's laws, which apply everywhere in the universe without exception. The speed of light is not a human limitation. It is the universe's limit, written into the geometry of space-time before the first star ignited. Every civilization that emerges on a rocky world around a main sequence star faces the same arithmetic, the same stellar clock, the same distance scales, the same exponential fuel demands, the same radiation environment, the same biological fragility. The question that the physics has been building toward, through every calculation, every failed theoretical loophole, every measured cost of acceleration, is not merely whether humanity can leave. It is whether the conditions that produce civilizations also reliably prevent them from surviving their own stellar neighborhoods long enough to cross the distances that separate them. That is not a question with a confirmed answer. It may be the most important question in science. There is a photograph taken on February 14, 1990, by the Voyager 1 spacecraft from a distance of approximately 6 billion kilometers from Earth. At the request of astronomer Carl Sagan, the mission team commanded the spacecraft to turn its camera back toward the inner solar system and photograph the planets it had left behind. Earth appears in that image as a pale blue dot, a point of light less than a single pixel in size, suspended in a beam of scattered sunlight against the deep black of space. The entire surface of the planet, every mountain range, every ocean, every city, every person who has ever lived, occupies a fraction of a pixel in a photograph taken from a distance that Voyager 1, traveling at 61,000 kilometers per hour, had required 12 years to cover. That distance, 6 billion kilometers, is less than one light day from Earth. The nearest star is approximately 1,500 light-years away in those same units. The pale blue dot photograph was taken from within the solar system's own front yard. Sagan wrote about that image in terms that have become among the most quoted passages in the literature of science communication. The scientific content beneath his words is what gives them their permanence. The photograph is not a philosophical exercise. It is a measurement, a calibration of scale. It shows, with the directness of geometry, that the entire inventory of human experience, everything that has ever happened, everyone who has ever thought or acted or suffered or created, is confined to a structure so small that a camera aboard a departing spacecraft could not resolve it as a disk at 6 billion kilometers. The confinement is not metaphorical, it is physical, and the physics of that confinement, as established across every domain of science examined in this film, does not yield to ambition or desire or the accumulated technological power of any civilization that has yet existed on this planet. The question is, what follows from that? One position, held by a number of serious scientists and thinkers, is that the confinement is permanent, that the barriers described in this film represent not merely current limitations, but fundamental constraints that no physically realizable technology will ever overcome, and that the long-term fate of intelligence in the universe is therefore to be born, flourish briefly in cosmological terms, and be extinguished by the death of its host star, leaving no trace that propagates beyond the boundaries of its home system. This is one interpretation of the Fermi paradox. The silence of the cosmos on this reading is the sound of confinement repeating itself across 2 trillion galaxies. A second position holds that the barriers are real but not necessarily permanent, that the current state of physics and engineering represents a snapshot of a civilization extraordinarily early in its technological development, and that the history of science is the history of limits that seemed absolute until they were not. The sound barrier was, for a brief period in the mid-20th century, spoken of in some quarters as a genuine physical limitation. It was not. The germ theory of disease was not obvious to medicine for most of human history. Nuclear energy was not a practical concept until the 20th century, despite the fact that the physics underpinning it had existed since the formation of the first stars. The argument from this position is not that any specific proposed technology, warp drives, wormholes, antimatter engines, will work. It is that the history of human engagement with physical constraints does not support confident predictions about the permanence of any particular barrier. Both positions are scientifically defensible. Neither can be resolved with current knowledge. This is not a rhetorical balance. It is an accurate description of the state of the evidence. What the evidence does establish, with high confidence, is the following. Humanity currently possesses no propulsion technology capable of reaching the nearest star within a human lifetime or within any time frame meaningful to a continuous civilization. The fastest spacecraft ever launched would require approximately 70,000 years to cover the distance to Proxima Centauri at its current velocity. Every proposed improvement to that figure, nuclear propulsion, fusion drives, laser sails, either remains at the concept stage, requires energy sources not currently accessible, or achieves velocities that reduce the journey to centuries rather than millennia, but still far exceed any continuous institutional memory human civilization has ever demonstrated. The longest continuously operating institution in human history, depending on how continuity is defined, is on the order of 1,000 to 2,000 years old. The Catholic Church, certain universities, specific monastic traditions. Nothing approaching the timescales required to plan, execute, and receive results from an interstellar mission at achievable velocities. The biological constraints are real and measurable, and currently unsolved. Long-duration human spaceflight beyond the protection of Earth's magnetosphere produces documented, quantified physiological changes across multiple organ systems. Bone density, cardiovascular function, vision, and potentially cognition are all affected by exposures that are brief relative to the duration of any interstellar mission. No pharmaceutical or engineering solution to any of these problems has been validated for the relevant timescales. The energy demands are not a matter of funding. They are a matter of physics. The Tsiolkovsky rocket equation does not have a budget parameter. The exponential relationship between desired velocity and required propellant mass is a mathematical consequence of conservation of momentum and does not negotiate. The theoretical loopholes, wormholes, warp drives, and their variants require either exotic matter with negative energy density in quantities that quantum field theory constrains to negligibility, or energy conditions that no known physical process can satisfy. They have not been dismissed by the scientific community as impossible in principle. They remain active areas of theoretical research. They have been established through rigorous analysis to face obstacles that are not engineering problems but physics problems, problems at the level of whether the universe contains the necessary ingredients, not merely whether we can assemble them. The sun will make Earth uninhabitable on timescales that are finite, calculable, and already in progress. The deadline is not imminent in any human sense. It is approximately 600 million to 1 billion years away for the first phase of solar brightening-induced surface sterilization, and approximately 5 billion years for the red giant expansion. These timescales are so vast that no current human institution, no current political structure, no current cultural continuity extends even 1,000th of the way toward them. And yet the physics does not care about human institutional timescales. The stellar clock runs independently of whether any civilization on the third planet is paying attention to it. There is a concept in long-term planning called deep time thinking, the cognitive and practical challenge of making decisions whose consequences operate on timescales far longer than any individual lifetime or institutional memory. Geology requires it. Climate science requires it. Nuclear waste management requires it. Evolutionary biology operates entirely within it. The challenge is not that human beings are incapable of reasoning about deep time. The geological record demonstrates that Earth scientists have reconstructed events from billions of years ago with extraordinary precision. The challenge is that planning for consequences on those timescales requires institutional continuity, resource commitment, and coordination across generations that no civilization has yet demonstrated in the domains that matter here. The civilization that will face the choice about what to do as solar luminosity makes the surface uninhabitable will not resemble ours in any detail. It will be separated from us by a gulf of time so large that the distance between ancient Sumer and the present day, approximately 5,000 years, is to that gulf what a single human heartbeat is to a human lifetime. The people who will face that deadline are not our descendants in any meaningful cultural or institutional sense. They are the future inhabitants of a planet that happens to be the same planet we are standing on. What connects us to them is physics. The same physics that constrains us will constrain them unless something changes in the understanding or application of that physics between now and then. And the only way something can change is if the work begins. Not the engineering, not the construction of vehicles that don't yet make sense to build, but the science. The fundamental research into the domains where the barriers are thickest, propulsion physics, exotic matter, quantum field theory, constraints on space-time geometry, long-duration life support, radiation biology, the mechanisms of biological aging in extreme environments. Most of that research is ongoing. The gravitational wave detectors are running. The James Webb Space Telescope is characterizing exoplanet atmospheres. Fusion research is producing results for the first time that justify cautious optimism. Quantum information science is probing the relationship between entanglement and space-time geometry in ways that were not conceptually accessible 20 years ago. None of it is close to solving the interstellar travel problem. All of it is necessary for any future approach to it. The pale blue dot exists at a specific address in the galaxy, the Orion Arm, roughly 26,000 light-years from the galactic center, orbiting the galactic core at approximately 220 kilometers per second, completing one full orbit approximately every 225 million years. This address has no particular distinction. It is not near the galactic center, where stellar density and radiation levels are prohibitively high. It is not in the outer halo, where stellar density is so low that planetary systems are rare. It is in the middle of the disk, in a relatively quiet region between spiral arms, with a moderately stable radiation environment and a sufficient density of heavy elements, formed in previous generations of stars that died before the sun was born, to permit the formation of rocky planets with complex chemistry. The sun is, in the language of stellar evolution, a third-generation star. The carbon in every living cell on Earth, the oxygen in every breath, the iron in every red blood cell, the calcium in every bone, none of it was produced in the sun. It was produced in stars that lived and died before the solar system formed, their outer layers expelled in supernova explosions or stellar winds that seeded the interstellar medium with the heavy elements that gravity later assembled into this solar system. Every atom heavier than hydrogen and helium in a human body has a history that predates Earth by billions of years. The universe manufactured the ingredients, and then, in at least one instance, those ingredients assembled themselves into something that could look back at the universe and wonder about it. That capacity to accumulate knowledge, to build predictive models of physical reality, to understand the structure of matter and energy across scales from subatomic particles to superclusters of galaxies, is, as far as all available evidence indicates, not common. It may not be rare in absolute terms across 2 trillion galaxies, but in the portion of the universe that is accessible to human observation, the evidence for it existing anywhere other than here is precisely zero. The radio telescopes have not heard an answer. The exoplanet atmospheres examined so far show no confirmed biosignature. The interstellar medium carries no artifact of any other technology. This does not mean we are alone. The universe is 13.8 billion years old and 2 trillion galaxies wide, and the search has been conducted with instruments of limited sensitivity for a period of decades. Absence of evidence across that search space is not evidence of absence. The statement is statistically trivial. We have searched an infinitesimal fraction of the available parameter space. What it means is that we cannot currently point to any other example of what we are. We have no second data point. We do not know whether the emergence of scientific intelligence is common or extraordinarily improbable, whether it typically survives long enough to become interstellar or typically does not, whether the silence of the cosmos reflects the rarity of minds or the rarity of minds that survive long enough to be heard. We are, in terms of confirmed evidence, the only known place where the universe has produced the capacity to understand itself. That is not a comfortable thought. It carries no guarantee of continuation. It implies no special protection from the physics described in this film. The rocket equation does not yield to significance. The stellar clock does not pause for the remarkable. The distances are the same whether or not anyone finds them beautiful. The Earth is 4.5 billion years old. It formed from a cloud of gas and dust left over from a previous generation of stars. It produced, after nearly 4 billion years of biological evolution, a species capable of deriving the equations that describe its own situation with precision, including the equations that describe the ceiling above it and the clock running beneath it. 300,000 years of that species. One pale blue dot. One star with a finite lifespan. One set of physical laws that applies equally everywhere. The universe offered no exemptions when it was assembled. It offers none now. What it offered, in at least one place, was awareness. The capacity to know the situation in full. The distances, the physics, the timescales, the constraints, and the questions that remain open. Whether that awareness is enough, whether it is the beginning of something or simply the most complex expression of something that has a well-defined end, the physics does not say. The physics has said everything else. That last question, it leaves open.